Hello, Trigonometry. This is your video lesson for lesson 16, solving trigonometric equations, day 2. So today we're just going to focus on some more complex equations. This lesson definitely builds on what was done in the past lesson, solving simple trigonometric functions. Taking a look at our first one, you can see right away that there are two terms that contain a trigonometric expression. When this happens and those terms can't be combined, we're looking at a problem that's going to require either factoring or replacement using some of our identities. In this case, we've got a squared term and a linear term, so this is a typical factoring problem. We're going to utilize a technique called substitution, and I'm going to use substitution because it leads directly into a calculus skill later on, and it's something you want to get comfortable with. So if we say that u is equal to cosine x, then over here we've got 2, and instead of cosine we put u squared, plus instead of cosine we put u, and then minus 1. Now this lesson really requires factoring skills from your previous math classes. How do you factor with a leading coefficient other than 1? There are a few techniques that you can use to accomplish this type of factoring. In general, I'm going to switch colors. You want to go for factor by grouping technique. There's also a few tips and tricks that you can use. So we're going to do A times C, and we're going to locate numbers that multiply to be -2 that can add to be 1. Thankfully for this example, I've chosen a pretty simple, straightforward pair of numbers. There's only one way to make 2, and that's with 2 and 1. And if you need those to add to be +1, the 1 is going to have to be negative. So we're going to rewrite our equation. Instead of being a trinomial with 3 terms, we're going to split it into a polynomial, replacing the plus u with an equivalent 2u minus u. Now keep in mind, 2u minus u is the same as plus u. That's why this technique works. Introduce one more color. We're now going to group our pairs with the first 2 terms and the last 2 terms and look for what's in common. 2u squared and 2u are both divisible by 2u. If we take the 2u out, our first term will be left with a u, and our second term will be left with a placeholder of 1. The idea when you're factoring is that you want to be able to distribute the terms back and get the same thing. 2u times u is 2u squared, and 2u times 1 is 2u. For our second pair, our second group, we have a -u minus 1, and so we're going to take out a minus 1, and that's going to leave us with u plus 1. Now this is how you know your factoring works. Both parentheses contain the terms u plus 1. This is the factoring step of factor by grouping. Our first factor is u plus 1, and our second factor are the coefficients that we're taking out. Now we're going to use something called the zero product property, which you've probably seen in a previous class. If 2 numbers multiply to equal 0, then either the first number is equal to 0 or the second number is equal to 0. And this is going to allow us to find our 2 solutions. For the first equation, add 1, divide by 2, and we get u is equal to 1/2. For our second equation, we just need to minus 1, so we get u is equal to -1. Now it's important with u substitution that you remember to bring the cosine back into your problem. U isn't just u, it's cosine x. Where on our unit circle, actually this doesn't define it, so we're going to find it for all real numbers. Where is cosine x equal to 0? Is it at pi halves, pi, 3 pi halves, or at the beginning when theta is equal to 0? The correct answers are that cosine is equal to 0 at pi halves and at 3 pi halves. And since those are pi away from each other, we can write this as a single answer, pi halves plus or minus pi n, because it'll keep repeating as you add pi. For our second equation, we've got u is equal to -1, which means that cosine x is equal to -1. Where on the unit circle is cosine x equal to -1? Is it 0, pi halves, pi, or 3 pi halves? The correct answer for this one is pi. And that's not going to repeat every 180 degrees or every pi, because when you add pi, you get +1 instead. So this one, we're going to add 2 pi it. And that's our final answer for the first example. So as you can see, these equations are much more complicated than the ones we solved previously in lesson 15. Example 2 actually has a lot going on. We have two trig functions like we did before, which is your clue that you're going to need to factor or use identities. But as you can see, these trig functions aren't the same. So they're not cosine and cosine or sine and sine. They're secant and tangent. So we need to use an identity that's going to allow us to replace one of these expressions with another and get the same terms. So think back to your Pythagorean identities, where the terms are squared, and find an identity for secant squared and tangent squared that we can use to replace what we've got. So the identity I'm thinking of is tangent squared plus 1 is equal to secant squared. And because it's equal to secant squared, I'm going to go ahead and replace the secant squared in my problem with tangent squared x plus 1. Distribute the 3 to both terms in the front parentheses. Oh no. Forgot to multiply the 1 by 3. Make sure you don't make that same mistake. Combine like terms, we can actually add 3 tangent squared x and -2 tangent squared x and just get tangent squared x. And then 3 combined with -4 is -1. And the nice thing about this one is even though it's squared, I don't have to factor it because the tangent is the only x in the entire problem. That means I can just add 1 and then square root both sides. Make sure whenever you square root, this is a really commonly missed portion of solving equations. So make sure you're doing plus or minus when you square root. Where on the unit circle is tan x equal to either positive or -1? And if you're stuck on tangent, go ahead and use your calculator and type inverse tangent of 1 and inverse tangent of -1, and this is going to give you a pretty good idea. I got 45 degrees for my first answer. And then I know this is also going to happen in quadrant 2 at 135 degrees. It's going to happen in quadrant 3 at 215 degrees. And it's going to happen, no, 225 degrees, sorry. And it's going to happen again in quadrant 4 at 315 degrees. So that means this answer is happening every 90 degrees. Rather than writing my answer 4 times with a plus or minus 360, or even 2 times with a plus or minus 180, I'm going to write my answer once and just use plus or minus 90. And for visual, just so we're on the same page, 45 degrees is here. You get the same answer at 135, but negative, and that's okay because negatives are allowed. You get the same answer down here at 225, that's positive, and then you get the same answer here at 315, and all of these are separated by 90-degree angles. All right. Example 3. 3 cosine squared x plus sine x is equal to 3. So we've got that same situation as the last problem where we have two different trig functions. We have a cosine and a sine. We're going to reach for a Pythagorean identity, specifically sine squared x plus cosine squared x is equal to 1. Rearranging this by subtracting sine to both sides, we get that cosine squared x can be replaced with a 1 minus sine squared x, and that's what we're going to do in our problem. Over here, we're going to get 1 minus sine squared x plus sine x is equal to 3. Distribute your 3 to both terms in your parentheses. And then from here, this is a factoring problem, so we want to bring all of our terms to the same side. I'm going to go ahead and subtract 3 from both sides, and that's actually going to cancel out both 3's. That leaves me with negative 3 sine squared x plus sine x equals 0, and I want to factor this. So what do these two terms have in common? 3 sine squared x and sine squared x are both carrying an extra sine x. In the first term, I'm going to be left with negative 3 sine x. For the second term, I'm going to be left with the placeholder 1. And I'm going to use the zero product property to set up two equations to solve for x. My first equation is that sine x is equal to 0, where on the unit circle is sine 0. Is it at pi halves, pi, 3 pi halves, or 2 pi? Sine is equal to 0, both at 2 pi, which actually I'm going to switch to be 0, and again at pi. And so this answer can be represented as plus or minus pi n, which will give me the answer 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, so on and so forth to infinity. For my second equation, it's going to take me a few more steps. I've got negative 3 sine x plus 1 equals 0. I'm actually going to add 3 sine x to the other side, and then divide both sides by 3. And so I've got 1/3 equals sine x. And if I ask you that question again, where on the unit circle is sine equal to 1/3? The correct answer is nowhere. So there's no unit circle angle that gives me a perfect 1/3. For this problem, I have to use inverse sine. 1/3, and I get the answer. That's about 19.5 degrees. Now be careful here, because that's in quadrant 1. But there's going to be an equivalent angle in quadrant 2 that has the same reference of 19.5 degrees. And so if we take 180 minus 19.5, we'll get our other answer in quadrant 2. And so we find that the missing angle is 160.5 degrees. And we can write both of these solutions the same way we wrote our first one, which would be 19.5 degrees. Oh, I should switch these to degrees as well. Plus or minus 360 n, and 160.5 plus or minus 360 n. And then I want to switch this answer to be plus or minus 180 n so that everything is in terms of degrees. So this is going to wrap up part 1 of the video notes for solving equations day 2. Thank you for watching.